Hi everyone, welcome back to another physics session. Today we're going to be looking at internal energy and specific latent heat. This session will be an hour long, and as always it will be recorded and uploaded onto YouTube if you miss anything or if you want to go over something again. If you don't know me already, my name is Preshayla. I study physics at Loughborough University and it's my 4th year as a tutor. And what we're going to cover today is talking about internal energy and kind of how temperature affects internal energy. So it's this new kind of energy that we've not seen before. Understand the differences in the two processes which result from a change in internal energy. Revise the specific heat capacity equation. And the reason I say revise is because we have met it before when we did energy, but I know that some of you were not in those webinars, so we will go through it and do some questions on it. We're going to learn two new equations for latent heat, which is again a new concept, and discuss the effect that temperature has on the pressure of a gas through experiment. We'll do our exam questions, and we'll have time for your guys' questions at the end. But if you do have any questions throughout the session, then don't hesitate to put them on the Q&A function or the chat function, and I will try to pick them up as I go along. Remember, you can submit it anonymously if you don't feel comfortable putting it on the main chat. Okay, so before we started the kind of recap of yesterday's webinar and the content for today, I just wanted to quickly remind you guys about the required practicals. Now, these are the required practicals for the AQA exam board, and they do differ between exam boards, but because my webinars are based on the AQA exam board, these are the ones that I will be teaching. So we have done most of them. We've gone through the specific heat capacity one, the insulator one, the resistance one, and so on and so forth. So we've done force and extension, force and acceleration. We've done most of them. The ones that we haven't done will be covered, don't worry, but I just wanted to remind you that they are there and they do need to be learned off by heart. Okay, so yesterday's webinar, what did we talk about? So first of all, we looked at density and the equation that governs density, which is mass divided by volume, a nice simple 3-component equation. Then we went on to looking at how we can measure the density of a solid, whether that be regular or irregular, by finding the mass of the solid and the volume of the solid. Then we went on to talk about the measuring of the density of a liquid. So again, measuring the mass of the liquid and the volume of the liquid. Then we went on to look at states of matter, which was kind of a nice refresher from year 7, year 8 science, which is solids, liquids and gases, how they're structured. Then we took it a little bit further and talked about the changes of state, so evaporation, boiling, melting, all those changes of state. And we talked about the conservation of mass, which is this weird idea which we kind of knew all along, but haven't really thought about in depth. And it's this idea of the conservation of mass. So when we melt an ice block into kind of a puddle of water, the mass of the ice block and the mass of the water is the same. The mass hasn't gone anywhere. Now that is not quite true, as one of you pointed out yesterday. The ice block, when it does melt, will evaporate off some water, and that will be lost to surroundings as water vapor. So yeah, conservation of mass, but there are kind of some little considerations that we need to make. Then we talked about the kinetic theory of matter. So the kinetic theory of matter is talking all about those particles, how they move, what the forces are between them, and we're going to expand on that a little bit more today. Talks about melting and boiling points, temperature time graphs, and how we can read melting and boiling points off of them. And we started a quick little introduction to latent heat. Now, all of this content was, I understand, quite a lot of content in a short amount of time, so please do go back and watch that webinar if you feel like you need a refresher. Okay, so starting with today's content, and we're talking about how increasing the temperature of a substance affects its internal energy. So what is internal energy, first of all? Internal energy is the energy inside a solid, inside a liquid, inside a gas. And it's made up of two components. One comes from the motion of the molecules, and one comes from the position of the molecules. Okay, so internal energy, two components which make it up. One comes from the motion of the particles, and one comes from the positions. Now, the one that comes from the motion of the particles is one that we're already familiar with. That's kinetic energy. We know that kinetic energy is the energy associated with movement. So, okay, we know that internal energy is made up of kinetic energy plus some other energy. Now, that other energy is known as potential energy. And it's this new energy that we've not met before. It's not gravitational potential and it's not elastic potential. It's a new kind of energy. And it's called potential energy. Okay, so potential energy is all about this idea of particles having some sort of energy which is associated with their positions. So potential energy is this energy which comes from the positions of the molecules in relation to each other. So internal energy equals kinetic energy plus potential energy. Note that this does not include the gravitational potential energy that the solid, liquid or gas might have, and it does not include the kinetic energy of the whole substance. Okay, so it only includes the kinetic energy of each of the individual particles and the potential energy of the positions of the particles. Okay, so because the particles are being held in a certain position, there must be an energy which is keeping them in that position. And that is what is known as potential energy. Okay, so it's this energy associated with the position of a particle that keeps the particle where it is. Okay, I'm just going to quickly share my screen to my PowerPoint so we can see it a little bit better. Okay, so moving on then to temperature. So how does increasing the temperature of a substance affect its internal energy? So when you switch a kettle on, the temperature of the water increases until the water boils. Okay, so when you switch a kettle on, the temperature increases. We know that. Until the water begins to boil. When the water begins to boil, there is no change in temperature. Okay, there is no change in temperature when the water starts to boil. When it's heating up, yes, there's a change in temperature, but as soon as it hits boiling point, as soon as it hits 100 degrees, the temperature does not change anymore. So how does this increase in temperature affect the increase in kinetic energy? Well, if we increase the temperature of our substance, we increase the kinetic energy. They're proportional to each other. If speed goes up, kinetic energy goes up. If kinetic energy goes up, speed goes up. And so these molecules get faster. They get more energy and they get faster because of this temperature. Now, when the water boils, the molecules gain enough energy to break away from each other and turn into a gas. Okay, so when the water boils, the molecules gain enough energy to break apart. They break those bonds and they start flying off and turning into a gas. Okay, so the energy stored by the molecules is called internal energy. So as we increase temperature, we increase kinetic energy, we increase speed, and they therefore have enough energy to break their bonds. Okay, so an increase in internal energy can lead to one of two things. It can either lead to the temperature of the substance increasing, or it can lead to the physical state of the substance changing. Okay, so the temperature of the substance increases, or the physical state changes. Okay, so two different things that can happen when we increase internal energy. And because there are two different things that can happen, there are two different processes and therefore two different equations. Now, one of the equations we've already met, and that is Q equals mc delta theta, or delta E equals mc delta theta. This is also known as the specific heat capacity equation. So, if you don't know already, delta E is the change in heat energy. M is mass. C is this new concept called specific heat capacity, which is a value. And that value tells us how much energy is needed to raise 1 kilogram of the substance by 1 degree. And delta theta is change in temperature. So remember, delta is this triangle, and the triangle means change in. So change in energy equals mass times specific heat capacity times change in temperature. Now, this process, this one of two processes, only works if the temperature is increasing and there is no change in state. Okay, so the solid might be getting hotter, but it hasn't turned to a liquid yet. The liquid might be boiling, but it hasn't boiled and turned into a gas yet. Okay, so it's really important that we understand the difference between these two processes. The first process is that the temperature of the substance increases, and therefore we use E equals mc delta theta. The other process now is that the physical state changes. The physical state of our substance changes. So it either goes from solid to liquid, or liquid to gas, or gas to liquid, liquid to solid. Okay, so any physical change in state uses this new equation. Now, with these two processes comes an association with energy. So if we are increasing the temperature of the substance, we're increasing the kinetic energy. If we're changing the physical state of the substance, we're changing the potential energy. Okay, so two different processes that we have and two different equations which govern them. So we know that for the first process, we have E equals mc delta theta, but for the second process, this physical change of state, we have to introduce a new equation. This equation will no longer work. And that's because it involves a change in temperature. This process does not involve a change in temperature. So our new equation is this. It's all to do with this new concept called latent heat. So latent heat of fusion is this idea of changing from a solid to a liquid. Okay, latent heat of fusion is this idea of changing from a solid to a liquid. Now, I'm putting emphasis on the fusion because there are two different types of latent heat. Latent heat of fusion and latent heat of vaporization, which we're going to look at in a second. So latent heat of fusion is changing from a solid to a liquid. Now, latent heat can also be described as the energy transferred when a substance changes state. So as we go from a solid to a liquid, what is the energy being transferred? It's the energy that is needed by the particles in the solid to break free and turn into a liquid. Okay, so in a solid, they're really rigid, they're really kind of strong forces between them. But when this latent heat of fusion comes in, it breaks apart the molecules and turns a solid into a liquid. Okay, so it's the energy that is needed to turn a kilogram of a solid into a kilogram of that liquid without changing the temperature. I can't stress that to you enough. When we change state, we do not change temperature. Okay, so latent heat has got nothing to do with temperature. It's all about just simply changing from one state to another. Okay, so when we turn from a solid to a liquid, we know that we have a melting point. And this melting point is when the change of state occurs. As soon as we hit melting point, we get the change in state. So we now need to introduce our equation. The equation for the specific latent heat of fusion is energy divided by mass. Okay, and we can rearrange this equation to give E equals mass times specific latent heat. So this is it in its symbol form, and this is it in its kind of word form. Specific latent heat is this symbol here, LF. So a big L for latent heat and a small f for fusion. So this is the equation that we use. Remember, E is just heat energy. Okay, so moving on to its kind of sister form, not exactly the same because now we're dealing with a liquid to a gas. And this is called the latent heat of vaporization. And it's going from a liquid to a gas. Again, it's the energy that is transferred when the substance changes state. It's the energy needed by the particles to break free. And it's the energy needed to change 1 kilogram of liquid into 1 kilogram of vapor without changing the temperature again. Okay, so it's the energy needed for the liquid to change state. Nothing to do with temperature. Now, this change of state occurs at boiling point. Previously, our change of state from a solid to a liquid occurred at melting point, but now we're talking about it changing from a liquid to a gas at boiling point. We have a very, very similar equation, but this time it's vaporization, sorry. Okay, so very, very similar equation. And you can see all I've done is changed fusion to vaporization and the F to a V. Okay, so very similar equations, but in an exam question, you would need to notice whether the question talks about a change of state from a solid to a liquid, or a change of state from a liquid to a gas. But in either case, the specific latent heat is the energy divided by the mass. Okay, so let's go a little bit more in depth to the idea of comparing the particles in solids, liquids, and gases. So, yesterday we talked about the kinetic theory of matter, and this is just building on it. So, in a solid, we have very strong forces of attraction, which is why the particles stay in the state that they do. In a solid, they also vibrate in fixed positions. When heated, the particles vibrate and can start to break away from their structure. When this happens, it's known as melting, and it can change state. In a liquid, we have weaker forces of attraction and a non-rigid structure because the forces are weaker. When a liquid is heated, again, some molecules can escape and turn into a gas. Okay, so if a liquid is heated, the particles get more energy and they can break their bonds and break away and turn into a gas. Then for a gas, the particles have high speed. Okay, high speed, but random direction. We can never predict mathematically which way they're going to go, how they're going to behave. Really, really random, okay? And because they are so random, they constantly collide with each other. So they're constantly moving around and constantly colliding with each other and the walls of the container that they're in. Now, because they collide, they create a force. So when two things collide, we know that there is a force between them. Now, this force is what causes what we know as pressure. So because of these collisions, because of the energy of the particles causing collisions, we get lots and lots of force. This force builds up and causes pressure. When we heat a gas more and more, it gains energy, it moves faster, it collides more, and the pressure goes up. So you can see that pressure is directly related to temperature, which is what we're going to talk about next. So, gas pressure and temperature. Why should you never heat food in a sealed can? Why do you think you should never heat food in a sealed can? Have a think about that. Put your answers in the chat. Why do you think you should never heat food in a sealed can? Few more seconds to have a think about what we have learned and how we can apply this to thinking about why you shouldn't heat food in a sealed can. Okay, so as we heat food in a sealed can, the temperature increases. We know that. So as the temperature increases, the particles gain more and more kinetic energy. Remember, temperature is directly related to kinetic energy. And kinetic energy is directly related to speed. So if we increase temperature, we increase kinetic energy and we increase speed. So it's kind of chain reaction. Now, if they are moving faster, they collide more. They collide with each other and they collide with the walls of the container. This creates lots of force, which add up to make pressure. Now, if this pressure keeps building and building as we keep heating and heating, there's going to be too much pressure in the can. And if there's too much pressure, there's too much force being exerted on the walls, on the inside walls of the can. And this may cause it to explode. Okay, so a reason why it might explode, and lots of you have said explode, but why does it explode? Well, the temperature increases, particles gain more energy, they move faster, they collide more, collide with each other and the walls, creates force and makes pressure. Okay, so this kind of chain reaction needs to be learnt by you, and you have to know the kind of knock-on effect of temperature. Now, okay, we know that pressure is created by force, but let's say we have a container, and the container is pretty big. It's a can of this size. It's a sealed can. Okay, and then we have a container that is much smaller. Now, I'm going to put some source of force in here because of my collisions of my particles. And I'm going to put the same amount of force in here because of my collisions of my particles. Okay, so the force in here is the same as the force in here, but the area of this container is much smaller than the left-hand side container. Now, which one has more pressure? Container 1 or container 2? They have the same force acting inside of them, but one is much smaller than the other. Which one has more pressure and why? Same amount of force, so why is there a different pressure? Okay, so there's more pressure in container 2. Although there's the same amount of force, there's a smaller area. And it's all done with this pressure equals force divided by area equation. Now, we're not going to go through this equation because we have done it before. And if you do want to have a look at that, then do go back and look at the webinar on pressure. But just as a reminder, pressure equals force divided by area. So to summarize, when temperature is increased, kinetic energy is increased and speed is increased. This then has a knock-on effect of the collisions and therefore pressure. And I've put the kinetic energy equation here to help you see that if kinetic energy goes up, speed must also go up. They are completely proportional to each other. Okay, so there is an experiment which relates pressure and temperature, which we can do. So in this diagram, you will be able to see that we have a water bath and a sort of spherical container, a funnel shape, with a thermometer in and a heater which is connected to the water bath. This tube is then connected to a pressure gauge. The pressure gauge simply tells us how much pressure is in this container. So we turn our heater on and we change the temperature. We increase the temperature. Okay. we do this in increments. So we might increase the temperature by 5, stop, breathe the pressure, 5 degrees again, stop, breathe the pressure, and so on. So all we're doing is changing the temperature. So temperature is our independent variable. Our dependent variable is pressure. Pressure depends on the temperature, which is what we're changing. Okay, now do bear in mind that in this experiment, you are heating the water in a water bath. Now that heat may not disperse evenly throughout the water bath. And so you must stir the water around to ensure that the heat is being spread evenly. So it's one consideration that you need to make in this experiment. So we can see that if we were to plot a graph of pressure against temperature, it makes a nice straight line. And that tells us that temperature is proportional to pressure. As temperature goes up, pressure goes up. So the person is changing it maybe in 20-degree intervals, 5-degree intervals, whatever. And he measures the pressure at each increment. And he plots it on a graph and does a line of best fit. Okay, so a simple experiment which can help us to understand what effect temperature has on pressure. Finally then, let's talk about the random motion of gases. So I've already said that gases move really randomly and we can't predict it mathematically. So how do we know that they move so randomly? We can't observe gases, we can't see air in kind of normal day-to-day life with our normal eyes. So we need to use a method which will allow us to see the random motion of the particles. So what we do is we take this kind of diagram here. So this diagram shows a glass cell which is being shone on by a light bulb. Okay, so we've got a glass kind of container here, completely see-through, and we fill that container with smoke. So we fill it with some smoke and we shine a light through the smoke. We then point our eye into the microscope, which allows us to see inside of the glass container. What we'll see is that the smoke is moving and constantly changing direction really, really randomly. So this allows us to see the particles moving around in a random motion. So again, you just fill the container with smoke, shine a light through it, you view it through a microscope, and you will be able to see that the smoke moves and constantly changes direction. So this gives rise to the random nature of gases. And the reason that we see this so well is because the smoke particles are much larger than the air molecules. And because the molecules are larger, they're easier to see. So the glass cell contains air molecules that are in constant random motion. As they collide with the smoke, they push it around and the direction of the push is completely random. So by using smoke, we are now able to see for ourselves and prove to ourselves that the motion of gas is really random. And you can take it one step further and research for yourselves Brownian motion. That's Brown with I-A-N. I'll just write it for you guys. So if you guys do want to kind of take it one step further and have a look for yourselves and research around the topic, if you are interested, it's called Brownian motion, and you can look it up and see more about why gases behave the way that they do. Okay, so that's all the content covered for today. Let's move on to some example questions. But before we do so, I'm just going to have a quick look at some questions. I know loads of you guys are putting on the Q&A that it's freezing up. I'm really sorry that's happened. I think it might be my internet speed. I'm on Virgin Media, and as you know, they've been having loads of problems. Please do let me know if it's still happening, and if there's anything that you missed completely, and I can go over it again. Okay, what's potential energy? Okay, potential energy is a new concept and can be quite hard to understand. So potential energy is a new energy, first of all. It's got no relation to gravitational potential and no relation to elastic potential. Potential energy is its new energy within itself. Okay, potential energy is the energy that is caused by holding particles in their positions. Okay, potential energy comes from the positions of molecules. Yeah, so potential energy is due to the positions of the molecules relative to each other. That's what potential energy is. And it's one of the parts that make up internal energy, which again is a new energy. So someone said, does GPE and EPE come under PE? No, gravitational potential energy and elastic energy are separate to potential energy. Okay, does the potential energy also increase through the first method? No. Okay, so this method here has only to do with the temperature of the substance. Okay, and the temperature of the substance is related to kinetic energy. The potential energy is only related to the position of the particles. Kinetic energy is related to the motion. Okay, so motion and position. So physical state changing is changing the position and therefore changing the potential energy. Temperature changing is changing the kinetic energy, and it deals with the motion of the particles. Two completely separate processes and two completely separate equations. One involves temperature, one involves physicality and the changing of the physical state. Okay, someone said they missed the explanation of delta E equals MC delta theta, so I will go through that again. Here's the equation delta E equals MC delta theta. So remember that delta is a Greek letter, but delta is this triangle here, and the triangle means change in energy, which is heat energy, equals mass times specific heat capacity times the change in temperature. So theta is temperature. Okay, temperature. C is specific heat capacity. Okay, specific heat capacity. Specific heat capacity is a property that is specific to a material. So copper has its own specific heat capacity, water has its own, and so on. Specific heat capacity is defined as the energy needed to raise 1 kilogram of a substance by 1 degree. Okay, so how much energy is needed to raise the temperature of that material? Specific latent heat, however, is defined as the energy needed for the material to change state without changing the temperature. Okay, someone said, what do you mean by new energy? Sorry if I confused you by saying new energy. I just mean that we're visiting a kind of a new energy that we've not seen before. So not a new found energy, it's always been there, just a new energy that we've not seen before in our webinars. So we've seen kinetic, we've seen gravitational potential, we've seen elastic, we've seen nuclear, but we've not met internal energy properly. So it's this new kind of energy that we're visiting. The same with potential energy. Okay, let's go through some more example questions, and then I'll take some more questions at the end if you guys do have any. Or if I've missed them, please do put them on again, because I might have missed them. Okay, so here we have the question that we looked at the end of yesterday's webinar. And this question is all to do with a model that a teacher gave a student to help them understand how the motion of a gas is. So the teacher put some ball bearings in a container, okay, and they had a motor which made the ball bearings move. So the first part of the question says, how is the motion of the ball bearings similar to the motion of the gas particles? Well, the thing that is similar about both of them is that it is random. Okay, so it's random. We never know in what kind of direction the ball bearings are going to move, as well as the fact that it's kind of in all directions, it's random. It also creates a pressure on the walls because they collide. So collisions and the random nature. Now, the second part of the question says, the faster the motor runs, the faster the ball bearings move. Increasing the speed of the motor is just like increasing the temperature of the gas. When we increase the temperature of the gas, we increase the speed of the particles. So use the model to predict what happens to the speed of the gas particles when the temperature of a gas is increased. So what do we think happens, or what do we know happens, when the temperature of a gas is increased? What happens to the speed of the gas? Put your answers in the chat. What happens to the speed of a gas when we increase the temperature of the gas? Loads of you are getting the right answer, which is that the speed increases. And some of you have even gone as far as to say that the speed increasing is due to the increase in kinetic energy, which is really good. So kinetic energy. So a change in temperature changes kinetic energy, which changes speed. Now it's important to look at it the other way around. So we've been talking about heating it, but if we cool our gas, we decrease the kinetic energy and decrease the speed. It's not a one-way system, it works both ways, and you kind of need to consider both ways in an exam. So these three kind of components of a gas are completely related to each other. They're all proportional to each other. Okay, these three things are very, very important when we're talking about gases. Temperature, kinetic energy, speed, and then you might add on pressure and force and collisions to the end if the exam question talks about pressure. Okay, so let's just go through one example of a specific heat capacity to refresh ourselves on how to do these calculations. I've put two here so that you can go through one at home by yourselves using the worked example that we're going to do together. So, calculate how much energy is needed to increase the temperature of 2 kilograms of water by 80 degrees, given that the specific heat capacity of water is 4,200 joules per Kelvin per kilogram degrees. So I will quickly remind you of the equation, which is E equals MC, M times C times the change in temperature. So have a go by yourselves using your calculators, or you may be able to do it by hand. What do you think the energy needed is to increase the temperature by 80 degrees of 2 kilograms of water, which has the specific heat capacity of 4,200? What is the energy needed? Let's see. Put your answers in the chat. So what is the energy needed? E equals mass times specific heat capacity times change in temperature. So you've been given mass, which is 2 kilograms. You've been given specific heat capacity, which is 4,200. And you've been given the change in temperature, which is 80. So when we times them all together, mass, 2, times specific heat capacity, 4,200, times 80, we get 672,000 joules. Okay, so energy equals 672 kilojoules if you wrote it like that. So all we're doing is E equals mass, 2, times C, 4,200, times 80. And do have a go at this other question by yourselves at home. Okay, so the next question talks about a balloon which is filled with helium gas. What is the movement of the particles of the helium gas inside the balloon? What is the movement of the particles inside the balloon? Knowing that it's a gas and knowing what you know about the movement of a gas. I'll give you 10 seconds to have a think. Okay, so the movement of the particles inside the balloons is completely random, so random motion with collisions with each other and the walls of the balloon. You could also say that they have high speed. Okay, so someone's just put in the chat, would they give us questions like this in the exam? Absolutely. These are all taken from past exam papers. Any question that I give you is taken from an exam paper. Okay, so really important that we know how to answer these perfectly. Okay, what name is given to the total kinetic energy and potential energy of all the particles of helium gas in the balloon? So we've met this energy today. What's it called? Okay, so hopefully you remember from the beginning of the session that the internal energy is the combination of the kinetic energy of the particles and the potential energy of the particles. So kinetic energy relates to the motion of the particles, potential energy relates to the position of the particles, completely separate. Okay, so again, potential energy is this idea that there is an energy associated with keeping the particles in their positions. Okay, an energy that is associated with the positions of the particles relative to each other. Okay, so this goes back to more of what we were covering yesterday, and I'm going to put it on the screen whilst I'm talking so that you have it for later on. And I want you guys to attempt this question at home, pause the video, attempt it using what you learned in yesterday's webinar. We won't go through it today, but I would like you guys to attempt it. Okay, so this picture shows a person taking a hot shower. There's a mirror in their bathroom, and when the person uses the shower, the mirror gets misty. But why does this happen? So I'm going to give you 30 seconds to have a think about why the mirror gets misty. We all know it happens, it's happened to all of us, but why? Few more seconds to have a think about why this is happening. Okay, so the first thing that happens in the shower is that the water evaporates. Okay, it turns to steam. Now, those water molecules go into the air. Okay, these water vapor molecules go into the air. Now, the mirror is cooler than the air. And because of this, when the water molecules hit the mirror, they lose energy. Remember, if we cool a gas, it loses kinetic energy. Now, because they've lost their energy, they cannot hold as many water molecules. And therefore, this causes condensation on the mirror. Okay, now there's another way that we can answer this question. So this is one way, and this is kind of one way to get the marks. Or you can say that the particles move closer together as they turn from a gas to a liquid. The mirror surface is heated and no condensation happens. Okay, so two different ways to look at this question, kind of opposite to each other. Okay, so we'll just go through one last question, I think, before we end. Okay, this is a good one to talk about. So, solids have a fixed shape and are difficult to compress. Gases will spread and fill the entire container and are easy to compress. Use your knowledge of the kinetic theory of matter to explain why this is the case. You should consider the spacing between the particles, the movement of individual particles, and the forces between the particles. Okay, so why is this the case? Well, the spacing between the particles in a solid is very, very close together. And because there's no air between, no kind of empty space between the particles, that makes it very difficult to squash. The same is the case in the opposite scenario with gases. They have a lot of empty space between them and therefore are really easy to squash. The movement of the individual particles is that they vibrate around a fixed point and they have strong forces of attraction, and the particles are held closely together and are not free to move around. With a gas, however, they move randomly, they spread out in all directions and fill the container. There's no forces of attraction between them and therefore they are easy to compress. So you need to reference all 3 points to be able to get all, I think it's 6 marks for this question. Okay, so really kind of easy to break down the marks. You have 3 different things that you need to point out for 2 different properties, so solids and gases. And as long as you mention all of them, you will be able to get all 6 marks. This is a really nice 6 marker. Okay, so we're going to end the session there. Please do have a go at the questions that I've pointed out along the way if you have time, as this will really help. But tomorrow we are going to be going over the last part of this topic and going to be doing lots and lots of exam practice. So you're going to be getting really used to the kind of questions. As always, this is recorded and will go up onto YouTube later. Yeah, so if you do want any more kind of one-to-one personal tutoring with a tutor like me, then that is something that my tutor offers. So if you feel like you want a kind of personalized situation, then we do offer personalized tutoring. So that's all from me for today, and I will see you guys tomorrow for another physics session.